this is kind of a vast subject. So why are bubbles and drops interesting to so many people? Because there are applications all over the place. Okay, so we know of industrial applications. Some of which we've already touched on. So inkjet printing, so microfluidics is it's basically the new field which involves moving around small volumes of fluid. And so this is important in drug delivery and so forth. So for example, you can buy a patch that will release a certain amount of chemical every day, and so you don't have to remember to take your pills and so forth. And digital microfluidics is the subset of microfluidics problems where the encapsulation is through surface tension. So basically you consider an individual drop as being a parcel, and it's contained within by its surface tension. Okay? And so here you can have, so we saw some bubble computers and so forth, but you can basically move drops through channels and, again, deliver them in various ways. You can encapsulate them on surfaces and sort them. So we showed these drops bouncing on the surface, and if you have different size drops, they'll basically all coalesce except drops of a certain size. And so you can use this as a filtering process. And we've seen, so when you're generating a spray for whatever, again, you're basically, these aerosols are simply small droplets. So one wants to be able to control the size of fluid volumes, and surface tension is critical. Okay? And now another rather lesser known area of application, which I think is very interesting, is in environmental flows. So bubbles and drops are also very important in the transfer of heat. Chemistry and biology. Between the atmosphere and the ocean. Okay, and so what it's, I think, particularly interesting is the role of biology, the role of bubbles and drops in biology, and this is because biomaterial, so whether it's spores or pathogens, viruses, typically this biomaterial is typically surface active, and so sticks to the surface of drops or bubbles. Okay, so if you're looking at how basically much of the heat, transfer of heat chemistry and biology happens in the surf zone, so where waves are breaking, and it happens there because there's a huge sort of chemical mixing. Fluid is mixed down into the water column. And bubbles break, and as we'll see, throw fluid everywhere, and this fluid oftentimes is a carrier of biomaterial. So if we start with bubbles, so we'll go through the life cycle first. How are bubbles born? So we can have vigorous interfacial mixing. So again, think of a plunging wave. As a wave plunges, it entrains air, and this gives rise to bubbles. If we look, okay, so this isn't a wave breaking, but it's a jet impinging on a fluid. And I don't think I can read. Can I play it? This is really annoying. Let me try. Oh, it depends on how big they are, I see. Really annoying. Hold on here. I just have to do this. Oh no, I really can't do anything. Okay, hold on. Unless I start playing it outside when I'm out of. Yeah, I need to minimize it, right? Even with the normal size, I can't reach the play button. So I'll just start it playing. And okay. Okay, so here's a plunging jet. So we just have a jet of one fluid going to another fluid. Again, this is same sort of topology as you have when water, a wave crashes, but of course it's much more regular and much lower Reynolds number. But you can see there's a sheet of air entrained, right? So you can ask the question, how quickly does the jet have to go to entrain air? But you see the generation of these small bubbles beneath the plunging jet. And so this is one origin of bubbles, is basically entrainment of fluid into fluid. And then, so here's another source of bubbles. Okay, so there's one, and you see that's also a source of drops, right? So you have one drop hitting a water surface, and you see the fracture. You see drops going everywhere, and then you have this bubble left behind. Okay? That's called a storm bubble. See note the buckling, the regular buckling here. I'm just about to publish a paper on that. So.
It's kind of curious that the
Yeah.
instead of just.
But think of it as a water bell, right?
Yeah.
Right? Because it's like we've actually solved that problem as well. You basically have a sheet shot upwards, and then you use the water bell equations to show that it closes. So basically, the nice thing about today's lecture sort of ties together everything we've learned. So water bell equations, Rayleigh-Taylor, Rayleigh-Plateau, because that's what's giving rise to all these instabilities, and then the Kulik speed. So if we look here, so here is very clear. You basically, it ejects a sheet, and this sheet then closes owing to the curvature, right? Giving rise to a storm bubble. So you could, in principle, solve this, right? And so then at the end, you see the rims developing and then pinching off through Rayleigh-Plateau. Okay, so that's one source of bubbles. So, for example, in the surf zone, another is cavitation. So, basically, if you have very high speed flows, if you have very high speed, then you have very low pressures. And if the pressure goes below the cavitation pressure, then you get the spontaneous formation of bubbles. We saw that in the case of the trigger shrimp. Less than the cavitation pressure, and so then you have bubbles forming. And this is very clear. But if you ever seen behind a propeller, you basically, they're inducing very high speed flows, and so you get you basically get a helical trail of bubbles behind the propeller. And you see, by the way, these bubbles, when they explode, they always scour. They damage the propeller because when a bubble explodes near a wall, there's a spike. And it gives rise to it basically, so you get pock marks all over the propellers. Okay? Okay, another one is the exsolution of gases dissolved in a fluid. So this we've all seen. When you open a Coke, if you have a bottle of Coke or something, especially if you shake it up, then when you open it, the bubbles come out of okay, and if you've ever done the experiment, if you have your bottle of Coke or whatever, and you open it, you can see nothing too exciting happens. But if you put a tablespoon of sugar in it, you ever done that? It just explodes, right? So basically, because the sugar acts as a nucleation site, and it basically means that so there are all these there's all these sort of rough structures in the fluid, and so these all serve as sources of bubbles, because the bubbles want to form, if they can save energy by forming in a corner, then they will, right? And so basically these these defects in the solids act as sources of bubbles, and so you just get huge streams of bubbles coming out of all of these corners. And again, it's because it's energetically less costly to create a bubble in a corner. Okay, and I'll show that in a second. The same is true in champagne. Okay, and so I'll show here champagne bubbles. So here, you'll notice when you're drinking champagne that the bubbles always come up in streams from individual points, right? They don't sort of form spontaneously within the glass or throughout the fluid bulk. They form on the walls. Okay, so here's we fill our glass with champagne, and you can see the bubbles always form at localized sites, right? And you basically get a stream of bubbles. And so those defects they're either little scratches on the glass, or they can be fiber from someone having cleaned the glass not so thoroughly. So this is a zoom. So they zoomed in on one of these nucleation sites. So, and in this particular case, so they zoom in on one of these to look to see what's happening there locally. And there's actually from a fiber from which they used in cleaning the glass had left a little something there. And so this is basically the fiber. So there's basically an element of material there, and you can see this is the source of the bubbles. But the same is true if you just have a crack in the glass or a scratch. You basically have these bubbles forming continuously in the inclusion. Okay, so now we can look at the life of the bubbles. So in particular, if we look at their dynamics, okay, so if we have our bubble now, and this is the same as generally true with so just for all intensive purposes, we can take the viscosity, the density to be 0. We have, let's imagine, so in most physical settings, we have gravity acting. And we've seen there are funny situations where there's surface tension gradients and so forth. But let's just assume we have a constant surface tension here. So our physical variables, if we do our Buckingham pi, can include these, but we're going to throw them out. And our units. Mass, length, and time. So we have, if we take these three things, then we're going to have three groups. So we have the Reynolds number, UA over nu, bond number, delta rho GA squared. I'm kind of cheating here a bit. I'm just going to use delta rho because we can then use the same numbers when we talk about drops, but you get the idea. And then we have the capillary number, which is viscous stresses to surface tension. So all of these we've seen many times in the course. And then if you want to take these into account, then you're going to have other parameters, right? Lambda 1 equals mu hat over mu. So this is mu is again rho times nu, and we can have lambda 2 equals rho rho. But basically these are the players here. Bond, capillary. And we can alternatively use another number we've seen. So again, any product of these guys is still going to be dimensionless, so we have a certain amount of freedom. So we can okay, so if we look at air bubbles in water, then we can characterize the system in terms of any of the two of these three parameters. And let's how do we do it here? So here we use bond number. Yeah, this is basically a bond number and Reynolds number. So when the bond number is small, things stay spherical owing to surface tension, and you basically have, so this is the Reynolds number here, bond number here, so this is basically how fast it's going and how big it is, right? And so you have spherical bubbles moving at low Reynolds number, and we can do the scaling very easily. And then as the drops become bigger, they get deformed in response to dynamic pressures. We've seen the onset. So first things go ellipsoidal, and then you get unsteady motion. So you get wobbling motion, you get spiraling motion, and then you get highly deformed shapes. The interesting thing is, and we'll go through this, but there's a limit where the bubble is very big, and it's a spherical cap, and it doesn't break up, and we'll see why in a moment. So it actually doesn't need surface tension to maintain it. Yep.
Useful number.
It's like the square root of the Bond number. Yeah. I find it very annoying where people just take a power of a dimensionless group and name it after themselves. But I don't think Yotbos actually did that. There's probably some student of his or something. There's an Ekman number, and the Ekman number to the power of -1/2 they call the Taylor number in rotating flows. It's like, come on. Got enough dimensionless group, surely. Okay, so this is air bubbles in water. That's the sort of big picture, and we can zoom in on certain aspects of it which we can rationalize. So air bubbles in water. There's a very nice book on this by. So this plot is from Grace, Clifton Weber. Okay, and so a few cases of interest. So do you guys all know how to do this? Rise speed of a small bubble. These are scaling arguments. If anyone's ever taken a course with me, they have to be able to do this scaling argument. Okay, so small bubbles. Small bubbles, say the Reynolds number is small and the Bond number is small. So, because the Bond number is small, surface tension wins, so it stays spherical. Okay, so the rise speed, what's the balance going to be? Right, so we have a drop of characteristic size A and it's spherical, moving at a speed u, so what's the characteristic viscous stress on it? So that's the characteristic viscous stress, and we have to integrate it over its surface. So we do that, and then we balance that with buoyancy. Right? So this is, so we call this rho. This is rho minus delta rho. So this is going to be delta rho G A cubed. Right? So that tells us that U goes as G primed A squared over nu. Okay? Where G primed is the reduced gravity. Okay, and so if you do this formally, then you find U equals, you can get the dependence of the viscosities. Okay, so here we're sort of assuming that it's the viscosity outside which is dominant. But if we have two phases, so let's imagine, so for the case of a drop, if you have two fluid phases, then you get the following. Okay, this is the Hadamard-Rosinski. Okay, and so mu here, lambda here is the ratio of viscosities. Okay, so in the limit of lambda going to 0, you get something which has the right scaling, right? But this is actually, so you can punch through this, so you basically have to solve for the flow inside and out, and you match them. And you do that, and so then what you find is that, so you see there's a very weak dependence, right? It's the difference between a drop and a bubble, because the limits, so if you explore the two limits of this, in the limit of lambda going to 0, which is a bubble, this gives 1/2 for this coefficient. And for the case of its being rigid, going to infinity, it gives 1/3. Okay, so there's a very small difference between the rise speed of a bubble and a rigid object. Of course, you have to non-dimensionalize. You have delta rho in there still. But you see that this dependence of viscosity, internal viscosity, is very weak. Okay, and the other interesting thing of note is that, and I mentioned this earlier, you would find when you look at bubbles, when you actually do experiments, you always tend to find the result that you expect for lambda being infinite rather than 0. And it's because the surface is acting as if it's rigidified. And this is because of the surfactants again. So we had that picture where we had surfactants being swept backwards by the flow and accumulating at the back. So then you have this gradient in surface tension, which rigidifies the surface. So again, this formula has long been established, but getting the limit of bubbles in the lab is very hard because you always get surfactant effects which act to rigidify the surface, and so then you get the result you'd expect where lambda is infinite rather than 0. Okay, so now as the bubble gets bigger, so bond number becomes order 1. So you expect distortions to set in. You guys did this on the first problem set. All right, so here you have stagnation points, which means low speed, high pressure. And here you have low pressure, so you have to have high curvature. So that's the first distortion. Okay, and so now, another interesting thing about bubbles, and you'd think, and this D.W. Moore solved this problem. That's a very nice problem. So you know, if you have high Reynolds number motion, and you want to solve for the flow around it, you say, well, high Reynolds number viscosity is not that important, so let's use potential flow. Okay. And you get into all sorts of trouble when you do that because you find that the drag on objects moving in potential flow is 0. Okay? But you might think, and the reason is you have a no slip condition which you can't take into account. So if you have a rigid object moving, then you get it wrong because the potential flow solution doesn't have a stagnation point. So you can basically solve for it, and it's moving by as if there's no drag whatsoever, right? But in fact, so if you impose the no-slip condition on the surface, then you actually generate vorticity, so you get this viscous boundary layer, where your potential flow solution doesn't work. And so you actually have to solve a boundary layer flow and then match it on to the external flow, and you find the dissipation in this boundary layer, and that's what gives you the drag on the object. Now, if you have a bubble, you might think, high Reynolds number bubble motion, we might be all right, because we have a free slip boundary condition there, right? So maybe, how does the potential flow do there? Well, it doesn't do much better. Okay, again, it predicts zero drag, and we know there is going to be drag. And the reason is the potential flow does not satisfy the free slip boundary condition. It doesn't satisfy the no slip boundary condition. You'd think it'd be better, right? You think potential flow, but if you actually calculate the potential flow around a sphere, it doesn't satisfy the free slip boundary condition. That is to say, the tangential stress at the surface of the bubble is not zero, and so again you need a boundary layer. You have a viscous boundary layer in order to satisfy the zero tangential stress boundary condition. Okay, and so then you have a viscous boundary layer. You calculate the dissipation in that boundary layer, and that's what gives you the drag on the bubble.
Because of surface tension, this tangential one?
No, it's just if you have a flow past a free surface, then you have so if this is Z and this is U, then you have du dz has to be equal to 0, right? So that's the viscous stress associated with the flow past a free surface, right? And so this flow along here has to have zero gradient in tangential velocity as it goes around the sphere, and that's not true for potential flow past the sphere. Okay? So potential flow past the sphere is wrong for flow past bubbles. This is it's wrong for flow past rigid surfaces. It's a different type of boundary layer, but you still need a viscous boundary layer. Okay? You okay with that?
Yeah, but it's interesting because that's
it's kind of subtle, right?
It's in contradiction with what we do with, say, Kelvin-Helmholtz instability, where you have a shear, you have a jump of velocity across the interface. But it's a little bit like modeling the bubble. Modeling the bubble as a vortex sheet.
So
which one could do.
Right, yeah, that's right. There is basically a vortex sheet, but you can still have. So you do, but yeah, you do have an interfacial boundary condition. Yeah. So you want to have this, right?
This is the vortex sheet problem.
So you have, but velocity has to be continuous at the interface, and you have to have a balance of viscous stresses.
Yeah, it's
right.
not continuous. It has a
Right.
jump.
Right.
This is what the model does.
Yeah. Right. Okay. So in any case, so we've seen here that even at the surface of a bubble, you get the generation of vorticity, right? And it's not entirely clear that that should be the case, but that's what influences the subsequent development. So as this thing rises, there's basically going to be viscous boundary layer developing here, and this viscous boundary layer is a source of vorticity, right? So you're basically generating flow around the bubble is generating vorticity. So the boundary layer on the bubble surface generates vorticity, and this vorticity accumulates in the form of a wake. Okay, so let's make our vorticity orange. This basically comes back here and accumulates and does something, and so there are different things that it can do depending on the Reynolds number. So if this is Reynolds number 10, you basically have the vorticity wraps up into a stable wake. Okay, so the flow basically looks like this. Again, we have our vorticity generated here and now accumulating here. Okay, but that can be stable up to a critical Reynolds number. Then above that, the wake goes unstable. You have two vortices beside each other, and they don't like it, and so they start. It goes unstable, and the thing starts. So these start getting shed. So just like if you look at flow past a cylinder at a certain speed, vortices start getting shed off the back, right? So it's stable for a while. Flow past this. So let me just draw this. Okay, so you basically then have it goes unstable, and these things are shed one at a time. Okay, and so we have flow past this bubble. We have wake instability. So this is Reynolds number around 50. And so this thing, so basically these are, again, vortices, so they're the sites of high speed and low pressure. So as they're released, you break the symmetry in the pressure distribution on the bubble, so it actually goes like this. So the bubble actually wobbles as it goes in response to these vortices being shed off the back. So again, if you have flow past a cylinder, you have same sort of thing. You have imagine this was a rigid object. You just have these things sitting there, would be fine. And then at a critical Reynolds number, this weight goes unstable, and you start releasing vortices, and these, because of their influence on the force on the object will actually start moving like this. Okay, and so this is true. So if you look at fireworks, you can tell what the Reynolds number is by by their path. So here we see. Okay, so this is a zigzag. So this is a 2D instability. So they basically go, the bubbles go like this, and then if you increase the Reynolds number further, then you get a helical wake. Okay, so you basically have this helix, this helical vortex being peeled off the back. Right, so the vorticity. So imagine if you're skinning an orange, right? You basically get and this again, and the geometry is such that this represents the vortex represents a point of high speed and low pressure, and so the drop is constantly moving in response to the dynamics of its wake.
In the fluid dynamics course that I give here, we see a little bit of this with complex variables. You can do some of this in the wake that John explained. You see the von Karman vortex street. Right,
exactly. I saw this great talk by this Frenchman, and he's saying it should not be called the von Karman vortex street. It should be called the Boulevard Bénard, because Bénard worked on it and was the first to do it. Bénard, yeah, it's always interesting how things get named after people. But so let me show you some videos of these wobbling bubbles.
Does it come out of Place d'Italie?
Which? It could be close near Hotel Jack. Oh God, now I can't play this one again. We've got the same problem. Engineering flaw. Oh, look at this. Now oh, see? Look. Perfect. I don't know if this is theoretically possible to do. So, right. So these are the paths of these bubbles, but they're basically moving and gliding, and it's also, so, this is really frustrating.
What's happening?
No, I can't hit the play button when the... Okay, I'm going to turn my laptop around here.
You should be able to project.
Yeah, no, but I can't. No, but I can't hit the play button when I'm in project mode. But so the things you have to understand here. This, by the way, so this is what happens with champagne. So a sign of a good champagne is that the bubbles move in a straight line, which means the Reynolds number is low enough, which means the bubble is small enough, right? And beer does this. If you look at beer, this is basically the beer regime. So it just means that beer bubbles are bigger than champagne bubbles.
You can't play here pushing F something.
F what?
F7?
Can you resize this screen?
Yeah. I give up. Anyways, these things drift slowly along on their nice heel. You'll have to take my word for it. But so if you have, see, it's funny because it depends on the size of the See, this one's no problem. So here, but here's a whole swarm of bubbles, and they're kind of, here you can see they're in a regime where they're being strongly distorted, but also kind of drifting. And these are, of course, there's so many of them, they're going to interact with each other's wakes.
So it's like a commercial of coffee beans.
Yeah, it does look, they look sort of like blood cells as well.
Yeah, that's
So, but this is something you can use in your everyday life to rationalize the Reynolds numbers of flows. So again, fireworks, depending on the size, sometimes they'll zigzag, sometimes they'll spiral, and the same thing for bubbles in drinks.
I have a doubt about this second configuration.
Hmm?
Because in the case of the cylinder, you know that there is a transversal dimension that is like different from the other one. But in this case of the bubble, you have a sphere, right?
Yeah, it's still two. The first instability is still 2D. It just goes. Okay, so and then if we so this is we're getting into the high Reynolds number regime, and we've done so we can do the scaling here. So let's assume the bond number is large enough that the thing stays together, but the speed we say. So what's the drag at high Reynolds number? Right. So rho u squared is characteristic pressure, a squared is a characteristic area, and that's going to balance buoyancy now. Okay, so this gives us u goes as square root of g primed a, which we've seen before. Okay, and same argument as we saw when we were talking about raindrops. Stagnation pressures will cause the bubble to cleave. That's to say, break the bubble. So it's basically a Weber number criterion. So if we sub in for u, then you find that the bubble will break. Okay, so again, the thing will break when you get bigger than the capillary length. Okay, so there is one exception here. Is the spherical cap bubble. So you can get huge spherical cap bubbles, this big, and it looks like this. So surface tension, although present, is irrelevant in the normal force balance. Okay, so this is for very high Reynolds. So this is air and water. If you have a big bubble, so bond number huge, Reynolds number huge. But on the surface, you have that rho u squared over 2. So on the streamline, P plus rho g z is constant. Okay. So this is basically a Bernoulli effect. So here, the streamlines look like this, and so the change in pressure due to the Bernoulli effect is being compensated by gravity. Okay. So you have basically a Bernoulli high here. And here you have the hydrostatic high. Okay, this is something Taylor looked at. Okay, and so you see that, so this is Bernoulli. So you see that surface tension is not needed for the integrity of the bubble. Okay, so that's one exception. The other can also get very large toroidal bubbles, and these we can also understand from what we've learned in the course. We know that if things are long and thin, they want to pinch off through the Rayleigh plateau instability. So how can you get large toroidal bubbles? Okay, so these are basically it looks like this, and you get quite large ones. I think we've seen them before in the course. I'll show you a couple of videos. But the reason these are stable is that they're embedded within a vortex. So if you remember, if you have Rayleigh plateau, imagine, so this is now embedded within a vortex, okay? So there's basically, you have a flow like this. So as the thing tries pinching off, it'll actually be stabilized by the rotation, right? Because rotation wants to throw heavy fluid outwards. So it doesn't want the heavy fluid coming in, which is what's needed for a Rayleigh plateau, okay? Okay, so that's the origin of these bubbles. And if you've ever seen, I have a video, I couldn't find it this morning, but dolphins make these, right? They're incredible, and dolphins make these, and they play around with them, and they break them with their noses. I can maybe take a look during the break. But this is basically what's happening. So you have a bubble which is incredibly, remarkably stable if you don't recognize the fact that it's sitting within a vortex ring, which is stabilizing it. Okay. We've got to find the one. I'm sure I can find it during break. But this is how this guy's doing it. So he's basically blowing a big toroidal bubble within a vortex ring.
Maar niet op commando en zeker niet zo vaak achter elkaar. Alia doet het gewoon voor de lol en kan behoorlijk goed mikken. Er zijn er die beweren dat de luchtbaan van haar geluk brengt.
Okay, so just a couple of other. Let's talk briefly about the death of bubbles. There's one. Let me show you a couple of things before we go to break. Just a curious bit of bubble trivia. So, turns out, so this was looked at by Charles Darwin's grandson. So, at high Reynolds number, he asked the question, if you have a bubble moving through a channel, so imagine we have an imaginary interface there separating two fluids, fluid A and fluid B. How much of fluid B will be transported forwards into fluid A? Okay, so we know that as this bubble passes, it's basically going to entrain some volume, right? Turns out that that volume is precisely equal to the added mass of the object. Okay? So this, we call this the drift volume. So if this volume of the object is V, then the volume transported forward is equal to the added mass. So this is in inviscid fluid mechanics. So this is added mass, which is kind of interesting. So for example, so Cm is equal to 1/2 for a sphere. Cm is equal to 1 for a cylinder. Have you run into added mass before? So added mass is basically the if you have an unsteady flow. For example, if you release a bubble into water, you can ask how quickly does it accelerate. And if you don't take into account added mass, then you find something ridiculous, like it's 1,000 times g, right? But the point is, there's resistance to its accelerating, because in order for it to accelerate, the fluid around it has to accelerate as well, right, to fill the void that it's leaving. And so it's basically a term, an inertial term resulting from the acceleration of the surrounding fluid. So it's very important in bubble problems. It's not important. So when is added mass important? Added mass is important when the kinetic energy of the surrounding fluid is comparable or larger than the kinetic energy of the object. So if you have a cannonball, for example, going into water, you don't have to worry about added mass, but you do have to worry about in bubble situations. But it's just sort of funny that it comes up here. And this was done, again, by Darwin, who is the grandson of Charles Darwin. So let's look at the death of bubbles. So we can have a slow, lingering death if their gas can just diffuse into the surrounding fluid. Not a glorious death. More interesting is rupture, because rupture will actually be the source will be the birth of droplets, which will take us to the second part of our talk. So if we look at this, so we can see in the slide basically what happens. Okay, so this is the death of one of these storm bubbles. So we have a bubble sitting at the surface. So basically you have this bubble sitting there and it's getting thinner and thinner and thinner until it finally ruptures. It'll typically rupture there, but it doesn't have to. Let's just imagine it does. So it's basically draining. So fluid is draining down until it gets to a critical thickness, and then it will rupture. Okay? And so then when it ruptures, okay, so here we have drainage, thinning, and then rupture. So let's say it breaks there. So what happens when it breaks? We see here the. Pardon me? Yeah.
Is that thing breaking? That's the breaking?
Yeah, so it breaks, this is breaks asymmetrically, but basically, if we imagine that it breaks here, we know that this hole is going to retract at the Kulik speed, right? So we know how fast it's going to go, and we know from the thickness, so we know its speed from the thickness, and then we know we have Rayleigh plateau developing on the edge, on the retracting rim, and this then, notice that as it accelerates around the rim, so this thing is going to go unstable, right, as it retracts, because you have the rim has fluctuations due to the Rayleigh plateau, and also as this thing's being pulled back, there's a centripetal force which is throwing fluid outwards, so which is why you get the drops being flung outwards, and these will, so you can get tendrils here, for example, and these then pinch off themselves to Rayleigh plateau. So you basically have this cascade of droplet formation. And so this is very important in the surf zone for generating like all the spray you get in the surf zone when you go to the beach. It's from this sort of dynamics.
And what is the motion set up, the speed of retraction?
Kulik speed. So that's...
Is that the same as that exercise of that thing that sort of, you pinched in and sort of over like this?
Yeah, exactly. Yeah, yeah.
How's it called?
So the Kulik speed, I'll write it down. So we saw there, if the Reynolds number, if the Onus-Orger number, that is, say, if viscosity is not important, which it typically isn't, hole retracts at the Kulik speed, and the Kulik speed you can get by scaling, but we actually solved it exactly, 2 sigma over rho h to the 1/2, rim grows. So that's going at the Kulik speed, which is set by the thickness of the film at the stage of rupture, and then the rim grows through entrainment, and then you get the sort of scalloping on the edge as Rayleigh plateau develops. Of edge, scalloping of edge, and then you get tendrils and drops. Tendrils, drops, and also, again, the centripetal force as the thing moves along a curve. Okay, and so this is actually, so it turns out disease transport in hot tubs. This is they're constantly bubbling hot tubs, and so this is, pathogens tend to stick to the surface to the interfaces, and so the extent to which pathogens are thrown throughout the air and throughout the room depends on this sort of dynamics. Because again, so if you get very small drops forming, then they can be suspended for a long time. Right? So. But these are some situations where this matters. Let's take a break, and we'll. Yeah.
Why is the speed of this configuration, the power configuration, is the same of that flat configuration where the thing unrolled like that?
What we did is we started there. We looked at the breaking of a film, right? We were doing.
The film, yeah.
Right. So basically, we started off with a film and we broke it here, right? We basically popped a film. And then it retracted like that.
But it was like,
so locally, this is what you have here, and then you have this additional curvature, right?
yeah, but I was just thinking, maybe I'm wrong, that the fact that that one was like a straight line moving like this, where this one is a circular thing like that, and here there might be a little more stiffness to the system, will be slightly slower than the flat one.
So,
is that wrong?
But it's not true. So in the viscous case, the geometry matters. This is something we looked at, but in the inviscid case, it doesn't matter too much. No.
If it's like this, or just
Yeah,
like that?
yeah. I mean, you certainly know. In the early stages, it's not going to matter, and
The early stages, no.
yeah, really, yeah, it doesn't too much. It only matters. there's a stage very early on where the geometry matters, but then there's a huge range in which it doesn't. So, but you can see, and again, so these things are, you have the possibility of Rayleigh-Plateau, but you also have the possibility of Rayleigh-Taylor, right? Because this thing's actually accelerating as it goes. So that's basically all you have to ever do in these things, is try and decide whether it's Rayleigh-Plateau or Rayleigh-Taylor. Okay?
Rayleigh-Taylor would do what here? So it's like a heavy fluid coming down?
Yeah, so if the acceleration of this, if this thing is being pulled down faster than g, right, then the effective gravity is upwards, and so then you have heavy fluid over light, so you have the potential of Rayleigh-Taylor instability.
So that would generate what, oscillations on like
Yeah,
this on
yeah.
the rim?
Yeah. Okay, so let's let's have a little break.